Okay, we will continue with the balancing of reciprocating masses. Today we will see what is balancing of inline engines, multi-cylinder inline engines. So you know all know what is multi-cylinder. Cylinder means there will be more than one cylinder in an engine. Normally all the automobiles now are multi-cylinder automobiles except for two-wheelers. So what is inline engine? Inline engine means if this is your axis of the crank, if this is your axis of the crank, all the cylinders will be on the one side of that crank. So if you view from here, all the cylinders are on the right side. This is known as an inline engine, or it can also be all the cylinders may be on the left side. It cannot be on zigzag fashion like this, one cylinder on here and next crank and the other cylinder here. This is not an inline engine. Inline engine means all the cylinders will be on the same side of the crankshaft. So that is what is known as inline engine. And I have drawn a diagram of an inline engine with four cylinders. You may be asked a numerical on six cylinders, five cylinders, four cylinders, or three cylinders. Approach is same. Here we need to consider if it is a four cylinder diagram as I have shown, first and the fourth cylinder, that is the first and the last cylinder, will be outer cylinder. That is written here, outer, and the cranks associated with that will be known as outer crank, and this will also be outer. So first and the fourth one in this diagram is outer crank. If you have six cylinder engines, then first and the sixth will be the outer cranks. And in this diagram, crank 2 and crank 3, that is representing cylinder 2 and 3 here, they will be inner crank, inner inner crank, and all these are rotating at different planes, and it is 1 2 3 4, the number of cylinder itself is planes. And what we need to do is we need to balance this engine, and here it is not partial balancing, it is, I have not written here partial balancing, it is complete balancing. That means if you remember from the last lecture, we need to balance balancing of primary as well as secondary forces, and since they are acting on different planes, there will be couples associated with forces and couples. So we need to balance primary and secondary forces and couples. It is not partial balancing, again it is complete balancing. In inline engines it is complete balancing. So if you remember from yesterday, we know primary unbalanced force. Primary unbalanced force acting on a reciprocating engine, if you remember yesterday, that will be Fp, and it is m into r into omega square cos theta. Theta is the crank angle. And secondary unbalanced force, which we neglected yesterday for partial balancing, secondary unbalanced force, that is Fs, S for secondary, F for force, and here P for primary, mr omega square. Only difference is instead of cos theta, that is cos 2 theta and divided by n, where n is the obliquity ratio, or simply n is equal to L by R, cutting rod length divided by radius of the crank. That's all. So obliquity ratio n. So this is primary unbalanced force. So since there is primary unbalanced force, and since these cranks are acting at different planes, there will be couples associated with. How do you find those couples? Like we did on rotating masses, we have to consider any one of these as a reference plane. Let's say one is reference plane, then everything right will be positive, everything left will be negative. So if you consider 2 as the reference plane, then like that earlier reference plane, everything right will be positive, everything left will be negative, and couples will be force times the length associated with the plane acting on the action and length from the reference plane. It will be either positive or negative according to the position of the plane. So I'm not going to consider any reference plane here because according to the numerical we may have to consider first, second, third or fourth as the reference plane, that you will see when we do a numerical. So third thing that we need to balance is primary unbalanced couple. We already know force, so couple will be nothing but, so CP I am writing couple for C and primary for P. So mr omega square cos theta and L, where L is the length from reference plane, like we did in the rotating masses. And fourth one will be secondary couple, secondary unbalanced couple. And secondary unbalanced couple will be nothing but CS, again couple C and S for secondary, mr omega square cos theta divided by, sorry, cos 2 theta divided by n, and an L for that length from the reference plane. So we need to balance all these four in order to get a complete balance. So how do we do this? So we need to, if we can do analytically, we need to find all the primary forces and equate it to zero. Rather than that, we will be doing is, we will be doing graphical method. That is, we will consider we will draw a force polygon of primary forces, and the closing side will be the unbalanced force, and we can find any one of the unknown masses like we did in the rotating masses. Then we have to draw the couple, primary unbalanced couple. Then if required, we need to draw the primary unbalanced force and primary unbalanced couple. So how do we do this? There is a slight adjustment that we want to do. So when you do the numerical, we will just modify this couple into dividing and multiplying by 4. So we will get m into r omega square L cos 2 theta by n. We will just modify this equation by multiplying and dividing by 4. So it will become mr, that 4 I am multiplying here and we are placing it as 4 by n, r by 4n, and 4 I am taking inside, and that 4 can be written as 2 omega whole square. So that 4 is taken, L into cos 2 theta. So this is the secondary couple. And if you compare it with the primary couple, which is mr omega square L cos theta, secondary, we, how we solve it is, we will consider a secondary crank position. So secondary crank, which is an imaginary crank, just to solving and to finding secondary unbalanced force, we are considering it as a secondary crank. It's an imaginary crank. The secondary crank will be having, when you compare these two equations, you see theta is double, will have angle is equal to 2 theta, r is equal to r by 4n, and velocity, angular velocity t is equal to 2 times omega. So the secondary crank will be at an angle 2 theta. This is the most important for us, because when you draw the secondary force polygon, when we draw for primary force polygon, we will take theta, that will be given in the numericals. But when you draw the secondary force polygon, you should take the same values of forces, but you should draw the polygon with a double angle. That means if it is first, for example, here first plane and second plane is at an angle 60. When you draw the force polygon of the primary unbalanced force, you should draw it for 60 degree. But when you draw it for secondary unbalanced force, you should draw it for 120 degree. Similarly, all the angles should be double to draw the secondary unbalanced force polygon. So this is how we approach a problem. We will see now how to do it graphically. Thank you.